morning, student. Today, in the series of abstract algebra, we are continuing with the polynomial ring. Myself, Dr. Govind Sharma. This is the last topic of ring. So, we are continuing with the polynomial ring. Here are some properties of polynomial rings and some important theorems today we will discuss. So, learning objective is the same for the polynomial rings. You understand about polynomial rings. So, now we start our lecture. If R is a commutative ring, then the ring Rf of polynomial over R is also commutative commutative. If R is a commutative ring, then the ring Rx of polynomial or R is also commutative ring. So let me start the proof. Proof. Let F and G are two elements. Of then approach G A0, A1, A2, A3 dot B0, B1, B2. You see the F and G are the collection of coefficient of x0, x to power 1, x to power 2, x to power 3. So A0, B0, A, A1, B1, AI0. I plus J here is equal to N. Simply, the multiplication of I plus j and sigma is equal to N. So we can write it this side V0, V1, V2, Vn dot A0, A1, A2. That way is equal to G dot. So Rx is commutative. So Rx is also commutative. Now, the second theorem second is if R ring R is the integral domain, if R is an integral domain, so its polynomial ring is also integral. Given that R is an integral domain, so its polynomial ring, we have to prove that the polynomial ring of R is also integral domain. For that integral domain, we know that integral domain, a ring is called integral domain if it is without zero divisor. If we take A element from R and B element from R, then if product A dot B is equal to 0, if and only if A is equal to 0 or B is equal to 0 or both is equal to 0. So we can say that there is, if R is integral domain, then there is no two elements exist that their product will be 0. The product will be 0. So now we take two elements from polynomial ring and we will show that their product will be 0 if one of them is equal to 0 or both are 0. So let we take let R be the integral domain. So it is commutative. So it is commutative ring with unity and Rx polynomial so we take f g below. Now f dot g a0 a1 a2 b0 b1 b2 so a0 b0 bg 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 and I plus j is equal to B0, B1, that we save become. And 1 is equal to 1, 0. In Rx, be identity element. So, so 1 dot f 1 0 0 a0 a1. So this can be write as a0 a1. All are 0, but only product of 1 is remaining here. So f dot 1 also we get. So Rx have identity elements. Identity element. Now, now we will show that now fx dot gf belongs to Rx and degree ff is equal to m and degree gx is equal to n. Fx can be written as I is equal to 0 to n. Am is not equal to 0. And similarly, gx can be written as 0 to n. Because the degree of fx is m, so xi, ai, xi is very long I to m. And in gx we can write down summation bi xj, bj xj or j vary from 1 to n because the degree of the polynomial is n. So now we will show that R the integral domain R the integral domain. So not equal to 0. That implies am dot Gyan must be That way we can say fx dot gx at x dot m plus n without zero coefficient. So fx dot gx is not equal to, so Rx, we can say Rx is the Rx with the integral integral. Now, one more important theorem, that if R is a ring and S be the set of R constant polynomial, in Rx. Then S is isomorphic S is isomorphic to R, that is given that so here R is a ring and X is the collection of all constant polynomials. So we will show here that R is isomorphic to S. R is isomorphic to S. For isomorphic, we know that we have to show a mapping from R to S. This is 1 onto an homomorphism. So here we get proof. Polynomial belongs to each constant. Each constant polynomial. So S is equal to x0 plus 0x plus belongs to. This is the collection of our constant polynomial. Now, first we have to show that show that f is R2, S is isomorph. Isomorph. So f is take R to F. F is equal to AF0 plus 0x plus 0x square belongs to R. Belongs to R. F of A, take f of A is equal to f of B. Then we will show that A is equal to B. So f of A is equal to AF0 plus 0x x square is equal to Bx0 plus 0x plus 0x square. So we get A is equal to B. That means f is 1. F is 1. So that means f is 1. Now simply we take S is the collection of constant polynomials. So we take f is a function, f is equal to AX0 and constant function, and f is equal to also constant. So f is equal to fg, then we get A is equal to B. Now now again A is equal to B. That means f is 1. Now we will show that f is on. For onto we will show that an inverse image of f is exists. So f of A, so now take f of A is equal to, so we can say f is again A plus. We can reflect by every action. So we can write like plus So it can be written as f of a plus can be written. So we get f of a plus b is equal to this is now for multiplication. Multiplication f a dot b is equal to ab f c. So this is a f 0. So this is can be written as f of a. uh, That means we can say we can say that f is 1 onto homomorphic. So f is isomorphic. So for isomorphic we will show here that image f from S to R is 1 onto homomorphic. Now we take the one example from reducible or irreducible from this type of question sometimes asked in the examination. So this is essential to do so that irreducible over Z7 plus 7. So here the question arises that x square plus 1 is reducible or irreducible. So solve this Z7. We know the Z7, the element of Z7 is equal to 0, 1, 2, 3, 4, 5. So for take element 0. So 0 square plus 7 is equal to 0. F2, F1, sorry, F1. We take is equal to 2. F2 is equal to 2 square plus 7. f3 is equal to 3 square plus 9 plus 7 is 1 and sorry 3 square plus 7 plus 1 is equal to and 10 is equal to 3. F4 is equal to 4 square plus 7 is equal to 1 is equal to again we get 3. F5 is equal to 5 square plus 7. So we get 5. F6 is equal to 6 square plus 7. We get 2. So we see that in this polynomial x square plus 1 for the mod 7 we get 1, 2, 5, 3, 2, but we never get for any value of from Z7 we get f is equal to 0. So f is equal to not 0 for for any a belongs to Z7. So the polynomial here is irreducible. Polynomial is irreducible. Okay, student. So this is irreducible polynomial. Similarly, we take another example. Pn is x square plus x plus 1 on z2. We know z is equal to z2 have the element 0 and 1. So first we find the value f0. So 0 square plus 0 plus 2. So we get f1. 1 square plus 2, 1 plus 2, you get 1. So in both cases we get f is equal to 1 when a belongs to in both cases we get 1 when a belongs to z. So so no value of no value there is there is exist not exist any a for this f is equal to. So again so it is now we do a question of reducible. How to find out the reducible? S cube minus 9 is reducible over So Z11 has the element 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So F0. We put F0, then 0 cube minus, or we can also write here F1, 1 cube plus 11 minus 9. So this is become F2, we put total cube plus 11 minus F cube is equal to 9 is equal to 0. So we find here A is equal to 3, for which F3 is equal to F of A is equal to. So this is reducible. You see? So this is the method to find the polynomial is reducible or not. This is important concept about polynomial ring because that type of question, a reducible ring or reducible polynomial or not reducible polynomial, is asked many times in the competitive exam. So this is important. Now come to our quiz question. Which is the true statement? A polynomial of commutative ring is also commutative polynomial. C polynomial. Ri is a field, then I is maximum ideal. A ring without zero divisor is called integral domain. So all are the true options. Okay, today we prove that theorem that a polynomial of commutative ring is also a commutative polynomial. Which is the truth about polynomial ring? Two polynomials are equal if AK is equal to BK. That's right. The all elements are equal, then we can say that the polynomial are equal polynomial or same polynomial. Similarly, polynomial coefficient D1. D1 is AK and B J minus K. So K minus J or J minus K. So here A1 B0 is B1 A0 is true. So both are true. This statement is true. R upon I is not the ring. R upon I is a ring. Definitely 2 plus is the maximal term. This is the right. B is the right option. Which statement is true? Isomorphic image of a simple ring? No. Isomorphic image of a division is division right. Z5 is a field. This is also right. So isomorphic image of field is also. And F plus and fifth A F A plus B is equal to F A plus A. Is also a homomorphism. This is right. So A option is the right option for this, and the previous one is the B, C, D. Three options are right. So thank you, students. Abstract algebra is near to close for now, and polynomial ring is finished. Our the polynomial ring. Now we will discuss some important question and practice the question on the basis of this phenomena and this concept. Thank you guys.